children, welcome to today's lesson on extraction of zinc. Have you ever thought why zinc is so important in our lives? Have you ever thought why we should produce zinc? It's hard to imagine a world without zinc. We rely on zinc as it has been found to be as essential element in the growth of humans and animals. It has been proved that a zinc-rich diet promotes fast healing of wounds. In agriculture, zinc compounds are used as a nutritive supplement to promote growth, in addition to their use as fungicides. Zinc is not regarded as inherently toxic. Metallic zinc is used in the production of alloys and in galvanizing to protect steel structures. It is still present as a chemical additive in rubber and paints. In the galvanizing process, the coating is applied by hot dip method or by electrodeposition. The latter gives a relatively thin coating that is usually used as a base for paint. Galvanizing is used to protect building structures or boat and machine elements.
Dear children, I am sure that you all know by now that zinc, Zn, is a metallic element found in group 12 of the periodic table. Its atomic number is 30 and relative atomic mass is 65.38. Zinc was known from ancient times when brass, that is an alloy of copper and zinc, was used. Lonius was the first to apply the term zinc correctly to the metal that we know today in 1697 AD. Today we will discuss in detail about extraction of zinc. Before we discuss any further, let us discuss the learning objectives for today's lesson.
On completion of this topic, learners will be able to describe occurrence and important ores of zinc. Explain extraction of zinc from its ore. Discuss environmental issues and environmental impact related to zinc production. List and discuss types and alloys of zinc. Explain applications of zinc. Solve questions.
Occurrence of zinc in nature. Dear children, let me tell you today about the occurrence of zinc in nature. Zinc is found as a mineral in the Earth's crust. It is usually associated with other base metals such as copper and lead. Zinc deposits are widely distributed throughout the world. The mineral is found in massive deposits where by far the largest tonnage occurs, usually has a high iron impurity content. The large sources are British Columbia in Canada, Utah, Colorado, Idaho in USA, Cerro de Pasco mine in Peru, and Broken Hill in Australia. The largest producers of this ore are Ontario and Quebec in Canada, Missouri in USA, Central Andes in Peru and Japan. Now let me ask you a question. Is zinc available in abundance or is rarely available? Let me tell you about it. Zinc, which is relatively rare in the Earth's crust, 0.007%, occurs mainly as the sulphide or the carbonate ore. Example, in the ores zinc blende and calamine respectively. Zinc does not occur in native form because it is a reactive metal. Let us have a look at an animation to understand this better.
Zinc ores are widely distributed throughout the world, although more than 40% of world's output originates in North America and Australia. The common zinc-containing minerals are the zinc sulphide known as zinc blende or sphalerite, ZnS, a ferrous form of zinc blende known as marmatite, ZnFeS, and a zinc carbonate known as calamine or smithsonite, ZnCO3. The main ores of zinc are zinc blende, ZnS, calamine, ZnCO3, zincite, ZnO, franklinite, ZnOFe2O3, and willemite, Zn2SiO4. The principal ore of zinc is zinc blende. In India, zinc blende is mined in Zwar mines located near Udaipur in Rajasthan.
Children, let us now learn about the extraction of zinc. Zinc can be extracted from zinc blende by the following steps: mining and concentrating. Zinc ores are recovered by many mining techniques ranging from open pit mining, mainly in the case of oxidized ore bodies which are located closer to the earth's surface, to the normal underground methods used for the more deeply located sulphide ores. The most common underground method of ore extraction is cut and fill stopping, in which tunnels are dug to moderate depths, branching away from the mine portals.
Concentration of the ore is done by the process of froth flotation, which is based on the principle of difference in wetting properties of the ore and the gangue particles with water and oil. The sulphide ore particles are preferentially wetted with by oil and the gangue particles by water. In this method, the powdered ore is mixed with water to form a suspension in a tank. Small quantities of collectors such as pine oil or eucalyptus oil and froth stabilizers such as Cresols and Aniline are added to the suspension. The mineral ore particles become wet by oil, whereas the gangue particles become wet by water. The water is agitated by a rotating paddle or by blowing air violently. As a result, the froth is formed. During this process, the ore particles which are preferentially wetted by oil becomes lighter. The froth carries the lighter ore particles along with it to the surface. The heavier impurities are left behind in water and these sink to the bottom. Since the ore particles float with the froth, this process is called as froth flotation process. The froth is either skimmed off from the surface or transferred into another tank. The froth is broken by adding some acid and the ore particles are separated by filtration and dried.
We now come to the process of extraction and refining, which includes roasting and sintering. Both of the main extraction methods for the production of zinc, electrolysis and smelting, require the prior removal of sulfur in a highly exothermic oxidation reaction. Concentrated ore is roasted in the presence of excess of air at about 1200 Kelvin to convert zinc sulphide into zinc oxide. For the electrolytic production of zinc, the roasting of concentrates is achieved in fluidized bed roasters, in which finely divided and heated particles of concentrate are suspended in a rising stream of air. The sulfur content can be reduced to less than 0.5% and sulfur dioxide gas evolved in it may be used in the manufacture of sulphuric acid. The process is thermally efficient and the resulting calcine is in the form of small particles that can easily be leached into solution for further treatment. Let us now come to the next process, that is the process of reduction. The process described before becomes difficult to operate if the grade of concentrant falls and particularly if the lead content rises above 3%. For this reason and because a strong lumpy feed is required, the zinc lead blast furnace utilizes a sintering process to supply its oxidized feed. This is fed onto a moving grate and fired in an updraft of air, and the sintered cake leaving the machine is broken into a convenient lump size. By virtue of the strength and hardness, sinter is an ideal feed for the blast furnace. Result is zinc oxide is reduced to zinc by heating with crushed coke at 673 Kelvin in a blast furnace. The vapors of the zinc formed are collected and condensed. Extraction and refining the zinc lead blast furnace.
Sintered zinc and lead concentrates mixed with metallurgical coke are charged into the top of a shaft furnace, into which preheated air is blown through nozzles or tuyers at the base. This procedure is similar to that followed in an iron blast furnace, with the important difference that the major products of reduction here are a zinc-bearing gas and liquid phases that separate in the furnace hearth and are tapped periodically. The liquids consist of molten lead containing recoverable copper and silver and the gangue content of the charge in the form of a molten oxide slag. The gas stream containing 8% zinc, 10% carbon dioxide and 20% carbon monoxide is directed from the upper shaft to a lead splash condenser, a chamber in which an intense shower of lead droplets is thrown up by rotors revolving in a pool of molten lead. The zinc vapor is absorbed into the lead, and by withdrawing the lead continuously and cooling it, the saturation point of zinc in lead is reached and molten zinc separates as a distinct layer on the surface. On removal of the zinc overflow, the partially cooled lead is returned to carry out further shock chilling. In existing smelters, shaft furnaces vary in areas from 15 to 27 square meters and capacities range from 50,000 to 1 lakh tons of zinc and 30,000 to 50,000 tons of lead per annum. The zinc-lead blast furnace has the flexibility to accept a wide range of mixed ores and residues in its feed. Complex sulphide ores have to be sintered, but oxides residues such as zinc ashes recovered from galvanizing processes, oxides produced from low-grade residues, lead smelter dusts and steel mill dust high in lead and zinc can bypass the sinter roasting process.
Let us now come to the process of refining, which includes electrolysis. The basic steps in this process include preparation of a zinc sulfate solution by leaching zinc oxide calcines, which are produced by the roasting of sulphide concentrates in dilute sulphuric acid. Refining of the resulting zinc sulfate solution and electrolysis of the purified solution. Let us now discuss about refining. The impure metal is refined by fractional distillation or by electrolytic method. Let us first discuss what happens in fractional distillation. The impure zinc contains impurity of cadmium boiling point is equal to 1073 Kelvin, lead boiling point 2024 Kelvin and iron boiling point 3273 Kelvin. The boiling point of zinc is 1183 Kelvin. The impure metal is distilled when zinc and cadmium with low boiling points distill over, leaving behind lead and iron. The boiling points of zinc and cadmium are also different, and therefore the mixture of zinc and cadmium is again subjected to fractional distillation when low boiling cadmium distills, leaving behind zinc metal in the distillation flask. High purity zinc is then run off from the bottom of the column. Let us have a look at an animation now to understand how this actually takes place.
Refining by using a fractionating column. Refining can be done using a fractionating column. When vapors of the mixture are passed over a fractionating column, then different metals are collected at different temperatures. At 1860 Kelvin, antimony is collected. At 1210 Kelvin, zinc is collected. At 1073 Kelvin, cadmium is collected. By electrolytic refining, let us now try to understand the process of electrolytic refining. In this process, the impure zinc is made anode, while a plate of pure zinc is made the cathode. The electrolyte is zinc sulfate, contains a small amount of dilute sulphuric acid. On passing current, zinc from the electrolyte is deposited at the cathode, while an equivalent amount of zinc from anode goes into the electrolyte. Therefore, pure zinc is obtained on cathode.
Children, now that we have learned so much, let us also discuss few environmental issues. Hygiene and pollution pose special problems in the process of extraction and purification of zinc. Extreme care has to be taken to work within existing hygiene standards. In the electrolytic refining method, atmospheric pollution is relatively easy to control, but liquid effluents and iron residues are more difficult to handle from the blast furnace wastes. The main waste produced by the blast furnace slag, is stable and can be dumped safely without affecting surface water. But since the blast furnace is also a lead smelter, stringent precautions for limiting lead contamination must be observed within and without the plant. Environmental impact. The production for sulfuric zinc ores produces large amounts of sulfur dioxide and cadmium vapor. Slag and other residues of process also contain significant amounts of heavy metals. About 11 lakh tons of metallic zinc and 1,30,000 tons of lead were mined and smelted in the Belgian towns of La Calamine and Plumberies between 1806 and 1882. The dumps of the past mining operations led significant amounts of zinc and cadmium, and as a result, the sediments of the Jeel River contain significant amounts of heavy metals. Levels of zinc in rivers flowing through industrial or mining areas can be as high as 20 ppm. Effective sewage treatment greatly reduces this. Concentrations of zinc as low as 2 ppm adversely affects the amount of oxygen that fish can carry in their blood. Soils contaminated with zinc through the mining of zinc containing ores, refining, or where zinc containing sludge is used as fertilizer can contain several grams of zinc per kilogram. Levels of zinc in excess of 500 ppm in soil interfere with the ability of plants to absorb other essential metals such as iron and manganese. Zinc levels of 2000 ppm to 1,80,000 ppm have been recorded in some soil samples. Let us now talk about the types of zinc which are available. Zinc is found in two special types. Zinc dust, which is prepared by melting zinc and then atomizing it with the blast of air. Granulated zinc, which is prepared by pouring molten zinc into cold water. Let us now discuss about the applications of zinc. Metallic zinc is used in the production of alloys and in galvanizing to protect steel structures. It is still present as a chemical additive in rubber and paints. In the galvanizing process, the coating is applied by hot dip method or by electrodeposition. The method of electrodeposition gives a relatively thin coating that is usually used as a base for paint. Galvanizing is used to protect building structures or boat and machine elements. Let us now discuss about anti-corrosion and batteries. Do you know that zinc is most commonly used as an anti-corrosion agent? Galvanization, which is the coating of iron or steel to protect the metals against corrosion, is the most familiar form of using zinc in this way. Zinc is more reactive than iron or steel and thus attracts almost all local oxidation until it completely corrodes away. A protective surface layer of oxide and carbonate forms as the zinc corrodes. This protection lasts even after the zinc layer is crushed but degrades through time as the zinc corrodes away. The zinc is applied electrochemically or as molten zinc by hot dip galvanizing or spraying. Galvanization is used on chain link, fencing, guardrails, suspensions, bridges, light posts, metal roofs, heat exchangers and car bodies. Let us now learn about sacrificial protection. Blocks of a more reactive metal, for example magnesium or zinc, are attached to the ship's hull or the underwater pipe. The magnesium or zinc can also be connected to a pipeline or oil rig by conducting cables. Sacrificial protection is similar to a displacement reaction with the electrons traveling from the more reactive metal to the steel either directly or through the conducting cable. This reverses the oxidation process. 3 zinc atoms in solid state give 3 zinc ions in aqueous state along with 6 electrons. That is, zinc is oxidized as it dissolves. Iron ions are reduced to iron atoms. Rusty steel is returned to iron metal. The block of zinc or magnesium is sacrificed to protect the steel from rusting and must be replaced before it all dissolves. This is less expensive than rebuilding the ship or replacing the pipe or oil rig.
Here in the picture, we find that bars of zinc are attached to hulls of ships and oil rigs. As you all are aware of the fact that zinc is above iron in the reactivity series, so it will react and get corroded first. The structure will be protected from rusting as long as zinc bars remain in contact with iron structure. Zinc has to be renewed after it gets rusted.
Let us further discuss the applications of zinc. With an electrochemical potential of minus 0.7618 volts, zinc makes a good material for the negative terminus or anode in batteries. Powdered zinc is used in this way in alkaline batteries, and sheets of zinc metal form the cases for and act as anodes. Brass is one of the most important zinc alloys and consists of a mixture of this element with copper. It is generally stronger and more ductile than copper. It has superior corrosion resistance and is widely used in water valves, hardware, instruments, and communication equipment. Rolled zinc forms part of the container of the common dry cell used to supply electrical current for small portable radios and flashlights. The more important zinc compounds are the oxide, ZNO, used in ceramics, rubber industries, and in ink production. Zinc sulphate, ZnSO4, is used in textile industry and the treatment of zinc deficiency in soils. Zinc chloride is used to preserve wood and as deodorant in several fluids. This compound is also used in dry cells and in paint production. We must also not forget the biological role of zinc. It is an essential trace element necessary for plants, animals, and microorganisms. Zinc is found in nearly 100 specific enzymes. The human body has 2 to 4 grams of zinc distributed throughout the body. Most zinc is in the brain, muscle, bones, kidney, and liver, with the highest concentrations in the prostate and parts of the eye. So now we come to the end of today's topic. Let us discuss a few questions. Let's start with this question. Now my first question is, consider the following reaction at 1000 degrees centigrade. Choose the correct statements at 1000 degrees centigrade. A. Zinc can be oxidized by carbon monoxide. B. Zinc oxide can be reduced by graphite. C. Both the statements A and B are true. D. Both the statements A and B are false. E. Carbon monoxide can be reduced by zinc. The answer is zinc oxide can be reduced by graphite. My next question is, extraction of zinc from zinc blende is achieved by A. Electrolytic reduction, B. Roasting followed by reduction with carbon, C. Roasting followed by reduction with other metal, D. Roasting followed by self-reduction. Yes, you are right. The correct answer is B. That is roasting followed by reduction with carbon. And now the next question is, match the following columns. Which one of them do you feel is correct? The answer is, the combination is A. Now let me ask you one more question. Copper can be extracted by hydrometallurgy but not zinc. Explain. The answer is, the standard reduction potential of zinc or iron is lower than that of copper, and hence both zinc and iron can displace copper from solutions of copper ion. Although zinc is a stronger reducing agent than iron, yet iron scrap is chiefly used in hydrometallurgy of copper because it is much cheaper than zinc. Iron in solid state reacts with copper ions to form ferrous ions in aqueous state and copper in solid state. In contrast, to displace zinc from solution of zinc ions, we need a more reactive metal than it. That is aluminium, magnesium, calcium, potassium. One more question is, at a site low-grade copper ores are available and zinc and iron scraps are also available. Which of two scraps will be more suitable for reducing the least copper ore and why? The answer is, the standard potential for the reduction reactions couple of zinc ion to zinc is equal to minus 0.76 is more negative than that of iron ion to iron redox couple. Therefore, zinc is more reactive than iron and hence reduction will be faster in case if zinc scraps are used. But zinc is a costlier metal than iron, so using iron scraps would be more economical. So I hope that you all have enjoyed today's lesson on extraction of zinc. I hope you have enjoyed the lesson as much as I have enjoyed.